Okay. So what is distributed system? That's a slide when I conclude the whole class. Okay. So a lot of you said you already mentioned you don't know what is it, but some of you have some ideas. I want to hear from you. What is a distributed system? Any examples? What you think about it when we are talking about distributed systems?
I have an idea.
Sure, go ahead.
It's like a system in which you have different computers linked through a network, and those could be physically in different locations or either in the same location, but in the end they are different computer systems.
Perfect. You just passed the course, okay? yeah, that's it. Really. What we're gonna discuss is like more detail about it, okay? Basically, it's multiple computers, as you mentioned. Let's just simply call them computers, but they are connected through the network. Network is big part and very important part of it, as I mentioned. Some courses. I'm sorry, just 1 minute. Network is an important topic there. So basically, multiple computers connected through the network doing something together. That's a basic definition for distributed systems. So they can be, of course, physically located in different places, because that's the whole idea. They are distributed. And why do we need distributed system? Or why not one computer to rule them all?
Well, yeah.
Yeah, go ahead. It's fine.
Me?
Yeah, go ahead.
I think a reason why it's better is more robust. Like if we have many working in the same thing and one or some of them crash down, the others can take the work that the other was doing. So a system can survive when there are difficulties. Well, that's a reason, I think.
Perfect. Fernanda, what do you wanted to say?
No, the same. If one breaks out or something, the other ones can help the same system.
Perfect. Yeah, that's one of them, failure, right? Because no matter how reliable we are making the systems, their failure still exists, right? There is no 100% reliability. Failure exists. So that's one of the reasons. What else?
To increase the speed?
Could be timing between.
Timing. You mean about the processing power, like the speed of the processing the data?
So they can serve they can scalability, right? The single fault tolerance, for example, that if one breaks, you can connect still to a web page, for example, right?
Yeah.
And networking connectivity, like how fast you can access the data, for example, in different locations.
True.
Right? Things like that.
Anyone wants, Juan, you wanted to add something?
Well, actually, it was kind of the same idea, because there is no timing between the systems or the servers, so they can exchange information no matter what, no matter which time is it. Something like that, I think.
Okay. Yeah, you almost cover all the things that I wanted to say. So there, I mean, as I mentioned, we cannot have 100% reliability. The failure exists. So they can be basically immune to the failure because they're distributed. There is no single point of failure, as Paul said. I mean, single computer, no matter how strong is that, is going to have a limited computation power, storage. No matter it's a supercomputer, it's still the computation power is limited. And another thing is physical location, right? Even if we can make a supercomputer 100% reliable, fastest processing, let's say in the world, that can process everything super fast, still there is a physical location problems, right? Because no matter how fast is it, okay, like let's imagine we are communicating basically by a speed of light, right? The signal pass through the coaxial cable, like fiber optics, by speed of light, almost. So even by that, even in that speed, still the distance matters between me as a client and server, where the server is located. Because we are talking about then like millisecond, nanosecond of delay, those are matters. So that's why we need distributed system. Not one computer can roll them all. So where we are using distributed system. Some examples of distributed system.
Web pages.
Web pages?
Yeah, when, like for example, at Amazon, you want to log in, you create a new client so you can connect.
Okay. Any more examples?
A lot
Maybe
of the
financial services.
Financial services? Anything that we all use in our daily life activities?
Internet.
Yeah. Mail services, email.
Okay.
services.
Yeah, those are basically all distributed system, right? The search that you do is happening through the distributed system. The shopping that you're performing in Amazon, your banking, your Dropbox, the music that you're listening, the Netflix that you're watching, those are all happening through the distributed systems. I mean, there is no other way, there's no any other way that we could achieve this type of performance from the Google, from Amazon, Dropbox, I don't know, Spotify, Netflix, YouTube, without distributed systems. So they are all basically, most of the, so when we're talking about cloud or cloud processing, cloud services, we are talking about distributed systems, basically. So that's why the cloud is not basically amorphous concept, right? It's not really cloud. So when we're talking about cloud, we are talking about big, massive storage places with a lot of connections, cooling systems, storage, right? So that's what we are, when we are talking about cloud, we are talking about distributed system, the system that distributed physically, globally, connected through the network, and they are really like physical structures. So just some examples. I mean, I don't need to spend more time there. So there are, for example, I mean, when we're talking about big companies like Facebook with all those massive amount of data that they're handling, we're talking about hundreds of thousands of physical servers, burning down like megawatts of energy per day and costing billions of dollars to basically install and manage. So what is the goal of the distributed system? As I mentioned when you were talking, it's like one of the key idea is to provide an abstraction level for programming. So for example, if you're developing some application using Amazon AWS, really you don't deal with all those complications about the network, about the communication, about the server location. You don't deal with any of those details that are happening behind the curtain. You just develop your programs, you run it, and everything is working, right? So one of the goals of distributed system is to provide that abstraction for us. And also about to hide the complexity for us as well. As you mentioned, distributed systems are scalable, they're more reliable, they're fault tolerant, they have very well-defined semantic, and they are very consistent. And basically, the last line, they do the heavy lifting for app developers. As I mentioned, you just developed apps. How all the board's going to access that application is none of your problems anymore, right? That distributed system are going to manage that for you. So they are the one doing the heavy lifting. You develop it. The rest is on them. So they provide that abstraction level. So that's basically the goal of the distributed system. I mean, in addition to providing us reliable, scalable, fast communications. Research results really matters when we're talking about distributed systems, because most of the things that you see existed, they came out of the research paper. They came out of the academia till become reality that we are using now. For example, NoSQL, which is a scalable non-relational database that can handle massive, huge amount of data. They came out of the research papers. That's why it's important for us to read the papers, to understand them very well. By like Dynamo that's coming, which is basically the backbone of the AWS, they all came as a research paper. They were all developed as a research papers to become a product later. So we going to read a lot of papers. Some of them are maybe 2, 3 of them from this Leslie Lamport, which is the most prestigious researcher in the distributed systems. I'm going to talk about him more. We're going to hear from him more. He's basically the god when we're talking about distributed system. He has a lot of papers, and all of them are basically groundbreaking papers. So yeah, he basically developed these papers a decade ago that was talking about the consensus problem. What is consensus? Is when multiple systems are getting agree on a particular decision. They take a unified decisions. And that is the consensus is very important concept in distributed systems, because without that, it would be total mess. Because a lot of, for example, when you, I don't know, when you do the transaction, it's just not just happening one place, it's updating a lot of other places, right? For example, you don't do a transaction here from your, I don't know, like Visa card, then you can just in the same second go do another purchase without, I mean, this data without being synchronized together. If there is no consensus about what is the balance of your account, you would either lose all your money or you would be spending more than you have, right? So that consensus for all those servers that distributed globally became an agreement about, that's just a dumb example, okay? But more, easy to understand. So that is very important topic. We're going to talk about this. And research papers are the one that came up with these things. MapReduce, which is the first paper we're going to read, basically it tells us how to process large volumes of data that are distributed over thousands of servers. This MapReduce paper is the one that started the whole big data industry. So this is basically the idea behind all those things that you might heard about Apache Hadoop, and all those big data industry came out of these papers. So this is the one going to be presented next week by your classmate. It would be great. All those things are developed on top of this idea, this paper. So let me pause it a little bit here. So we were talking about this, this first. Today, I wanted to talk about basically the network communication. I don't know how well you are, how well is your background on the network communications. I can actually add, if you are interested, I can add you to like a Cisco Academy class. If anyone is interested to take voluntary network class, okay, you can do that. I can add you to the class, and you can take the class by yourself in order to learn more. That's totally optional. So today is supposed to talk about basically the communication part of the distributed systems. As I mentioned, some universities, they totally focus on network communication when they talk about distributed system. Basically, they're talking about the backbone of the distributed system. But I just want to dedicate this class for this very brief discussion about it. talk about a little bit about network communication and remote procedures call. So the problem of communication. Let's first talk about how we humans are communicating. For example, I'm from Iran. I speak Persian, but I'm talking to you in English because if I شروع کنم به فارسی حرف زدن مطمئناً شما هیچی نمیفهمید. درسته؟ So I need to talk in a language that we are agreed on certain rules and regulation in order to make the communications. So I just talked to you in Persian for a little bit. So that's the same thing happening with the process and in two different hosts or client servers. That's the same problem we are dealing with when we're talking about the communications. So basically, the host A and B, they must agree on the meaning of the bits sent through the medium. So for example, about the voltage, about modulation and all those things, synchronization, preambling and all those details that two hosts need to agree on in order to be able to communicate with each other. Like me and you, we are agreed on this little bit of delay between each word that I'm saying, define the words, this is the way we pronounce it. So I'm not native speaker, I may sound weird for you, but still, I hope you understand my English. My accent doesn't bother you much. If by the way, if you feel I'm talking too fast, or I can slow down, or you just tell me if you had problem understanding me. So it's the same thing happening between two hosts when we're talking about the communications. So another issue that we have a lot of applications, tons of applications, different type of transmission medium, coaxial cable, fiber optic, Wi-Fi, and it's and the idea is we cannot really implement every application for every particular transmission medium, right? We cannot have one HTTP for coaxial cable, one for fiber optic, and one for Wi-Fi. Because in Wi-Fi, we are using radio frequency. In fiber optic, we are using electrical pulses. In coaxial cable, we are using voltage in order to transfer messages. So, but what we are doing is we are not having one HTTP for each of these transmission medium. And what is the solution to avoid this problem? To have intermediate layers. So that's where layerings come from the whole idea of layering in the network connection, OSI or OC layering or internet layering. The idea comes from here. Because if we have this intermediate layer, then I just need to develop HTTP, Skype, like FTP for for these intermediate layers. Sorry. It was my mistake. I just taught her how to jump on the table. So we don't do that. So we have these intermediate layers that I just develop my protocols to be used by these intermediate layers, and then that intermediate layers will communicate with all the transmission medium. So that's why the layering come from. So in the internet, we have physical layers, link layer, network layer, transport layer, then applications. In OCI, we have session presentation layer as well. Sorry, I'm going fast. These are the details will be available in the slides for you. If you have problem understanding them, please refer to that, okay? So I'm just trying to stick with the schedule that we're going to have. So that's how the communication happens between each layers. We have host A, we have our intermediate routers in order to send our data to host B. And in network, each layers communicate with the peer layer. These are just background. I mean, not important so far. Not important to distributed system. I mean, just more on the network side of it. So the communication happens this way. Each layers provide services for the layers sitting on top of it. The communication goes from the packet goes from application layer to the transport network and physical layers. So So each layer is basically adding its own headers to the packets and passing it through the layer sitting on top of it. And basically the transport layers does the encapsulation of the application layer message. And the same for the network, then that transport layer packets becomes basically encapsulated in the network layers header. So let's see.
A header is or
Questions?
a header is a kind of protocol.
Pardon?
And when you write this message, when you put a header, the header is a protocol.
No, header is basically encapsulated encapsulated data. Okay. For example, the data that you have here in the network layer or datagram that you have in the network layer, this header is the header of the network layer. For example, information about the routing, which route to take, the source IP, destination IP address, okay? And then inside this encapsulated datagram, there are a lot of information about transport layer. Are you using FTP? Are you using, sorry, not FTP's application. Are you using TCP protocol? Are you using UDP protocol, different protocol for transport layers? So basically TCP is for reliable data transfer. UDP is more lighter, faster for live transmissions. So those data basically will be encapsulated here. So then in addition to those, we have sockets, okay, that basically is, it's included, basically each process in your computer has its own basically dedicated IP port. Not the IP is the same, but it has different ports, each process communicating through that port. And then in order to do that, basically what we used to do all the time is we used to do socket programming. I don't know if anyone of you had ever done something like that. Yes, all. So socket programming is something like this. Oh my, that's fine. It was my phone. So socket programming is it's hard. It's not easy. Okay.
It's raining here.
So socket programming is it's not again that easy, and it's not that convenient for programmers. There's still lots of it's a lot for programmers to deal with every time that they want to develop applications to do the socket programming. So far, it's more background, okay? No, don't worry about it. And don't feel that you're lost. So the whole idea is basically how to separate different requests on the same connections by using the socket programming. And how to write bytes on the network, read bytes from the network using socket programming, and what to do with those bytes that you're receiving or sending. So socket programming is still pretty painful, have to worry a lot about the detail of the network. So what was the solution about? The solution coming up with another imaginary layer, calling it RPC, remote procedure calls. The idea from remote procedure call is, as in like a typical programmer, usually that's how we learn programming, running a certain basically single-threaded code in a personal systems, right? In a, how to say, single-threaded code that runs in one place. That's how we train or learn programming initially, right? But the goal of RPC is to make this, let's say, programming for distributed system more like a programming for a local device. So that's the idea of having remote procedure calls, so that we can do things through that remote procedure calls that gives us this sensation that we are just running our program in our computer. Okay. So everyone uses remote procedure calls. I mean, you might not know that you're using it, but you're using it always. I mean, for most of the programs that you're using it. These programmings in these labs or Go programming that you're going to use, you are going to use remote procedure calls. So don't worry about that. You're going to learn it as we are going through. So as I mentioned again, the goal is giving this feeling to us that we are running a single program, a single processor, like a single process or single threaded computer, or more like a procedure call that we used to do in a normal programming. So in the normal programming, you have a caller, you have a callee, caller push the arguments into the stack, then jump the address to the callee function. Callee reads the arguments from the stack, right? Executes, put the return value in the register, then returns to the next instructor to the caller. And then caller is going to get that basically result back. But this is basically a normal procedure calls in one computer, all the programming languages almost. So the remote procedure calls goal is to make communication appears like a local procedure call. So we don't basically get involved with the details, with all those small details for the network, for distributed systems, or all those remote connections and communication and fetching data from, let's say, cloud. So we don't want to deal with that. So remote procedure calls going to make that possible. But yet, there are some certain issues involved with RPCs. For example, one is heterogeneity. So a client needs to rendezvous with the server. Server must dispatch the required functions. So the problem would be like, what if the server is different type of machines? For example, you're having RPC in a Windows, your server is running on the Linux, or it's a Mac. So another issue with RPCs is failure. What if the message got dropped on the way? The message didn't deliver to the basically the server or to the host B. Or what if the client server or network fails? Each of these components of one, let's say, distributed system. We have a host A, we have a network connection to the host B. So we have two different hosts distributed physically connected to the network. So all of those components can fail. Network can fail, host A can fail, host B can fail. So how are we going to deal with this type of problems? Also about the performance. For example, a procedure call in a normal computer takes around 10 CPU cycles or 3 nanoseconds. Then RPCs in data centers take around 10 microseconds or 10 to the power of 3 slower than the procedure calls. And in a wide area distributed like systems, not just inside one data center, it can take up to milliseconds to do that call. So you can see we are dealing with the performance, we are dealing with the delays, because it's not, again, your call, it's not a procedure call that's happening inside one CPU or one system that can do that in a nanosecond. We're communicating still physically, let's say from me sitting in my house from a server located in the United States or another part of the globe. So those are some issues. So, and there are more issues like difference in data representations, which is not an issue for local procedure calls because it's all developed using same method or same type of data representation in same systems. Those can be issue or problems for remote procedure calls. For example, maybe processes are run in different languages. Data types are different sizes. For example, different byte of ordering or endians. I don't know if you know that concept, endians. You have two like little endians, big endians. Basically, the idea is you give, you start with lesser significant bits first, or you start with most significant bit first. So we have both type of data representations. So those type of things can be like issue in remote procedure calls. So what is the solution for that? Solution for this type of issue is interface description languages. So far what we are talking about the network that enables us to have distributed system, what we needed to do with the network in order to be able to do like remote procedure calls. For example, I'm calling a procedure that doesn't exist in my system. It exists in a server of a Google or my Dropbox server, right? That I'm editing one documents. I'm doing some procedure call, but the procedure is not located in my system, is located in another systems. So that's the idea. But in order to come up for solution with those issues, we can have interface description languages, which is basically mechanism to pass procedure parameters and return value in machine independent ways. So we don't want to deal with those things that each machine is different with other machine in terms of data representations, how we are dealing with basically those things that I mentioned here, like endians, different size for different type, different data alignment, all those details. So programmers may write an interface description in IDL or interface descriptive language. So basically what they do, they define API for procedure calls. They have a name, parameters, and return times. So basically it's more like simplified. So then runs an ideal compilers, which generates code to Marshall. Marshall means convert native data types into machine independent byte strings. So basically what we are doing here for those remote procedure calls, we're making those calls in a way that they are not dependent on any language or any machines. They're totally independent of those details. So for that reason, we can basically transfer them to the host B or the server, and the data can get there to the server, be unmarshalled or convert to the local way of data representations in order for the server to be able to process our request. So let me show you here. It makes it much more simpler. So this is a day in life of an RPC, what's happening. Let's say we have a client machine, we have a server. What we want to do, we want to add 3 and 5. Maybe it's super complicated something, we don't need a server for that, or I'm doing that in a remote procedure call anyway. So I call that process, okay? Client calls the stop functions. For this procedure, so it will be basically stop Marshall's parameters into the network message, then pass it to the client OS operating system. OS sends the network message to the server. That network message arrives to the server. It becomes basically unmarshalled parameters and call the server function. So the server's function runs, return the value is 8. The 8 will be returned to the client, right? So it will be, again, it needed to marshal the data, basically making it independent of the machines that is run on, send it the data back to the client machine, and all the way that to the client process to get the value.
So I'm sorry, I have a question. So the Marshall, let's say the Marshall feature happens in both sides, right? In the client and in the server.
Yes, exactly. So when basically we marshal, the marshalling is like converting data, making it like a machine independent data, way of representation data. And then in the receiver, it will be unmarshalled, it will be converted in a way that the receiver machine can read it, and vice versa.
Okay.
So far, what I'm talking is just background. Basically, most of this thing that I'm talking, I told you just now, it's going to be, we're going to put it away when we start talking about other issues in distributed systems. So there's the server stub is really two parts. You have a dispatcher that receives the client RPC request, and the skeleton that does the marshalling, calls the local server procedure, and the marshal that returns them back. I mean, nothing important. What is important here, all these details that I'm talking about, why you never heard of it, because you don't need to know these things in order to call those RPCs. You don't need to know any of those details in order to do to develop a program to run it globally, accessed by all the people in the world. You don't need to know any of these issues. That's why all these are hidden from the client, from the users. So these remote procedure calls I mentioned, they can fail. Okay, things can go wrong with remote procedure calls. Client may crash and reboot. Packet may be dropped because it's passing through the network. A lot of packet drops happening there for so many different reasons. Packet may get lost. The routing table might be broken. The packet doesn't arrive at all. Server may crash and reboot.
Professor.
Yes, go ahead.
Just a quick question. With packet or packages, you mean data packages, right?
Yes, yes.
Okay.
Yes, for example, here I'm talking about, let's say, an RPC remote procedure call packets. So you call this at 3 and 5, and you send it to the server to process, okay? So this packet can be dropped because client, before sending the packet, client can crash and reboot. Before arriving, maybe it arrived to the server, but the server suddenly crashed and reboot, or maybe the packet never arrived because the network had problem. Or network or server might be just very slow. The connection might be facing some delays for any possible reason. But the question, the point here is all of this may look same to the client. Client has no idea why when I call this procedure at 3 and 5, I never get response. For client just knows I didn't get response. I don't know what happened, right? The packet dropped, server crashed. I don't know. I didn't just get the response. All this looks the same for the client. So, okay. So the failures from client perspective can look like this. Client sends a request. The server get the request, process, answers, does the reply, but the reply never get to the client. That is hidden from the client. The client doesn't know the packet dropped, the server got crashed, the reply got dropped, no idea, right? You have no information about that. But there are certain ways to deal with those problems. Namely, we have 3 different message delivery schemes. Anyone is familiar with this? In network course? No? So we have different schemes at most ones that we have sender and receiver, and message is lost. We have at least once, okay? So basically the idea here is the sender can keep track of the state of the packet using the reply method, acknowledgement. And exactly once is where sender and receiver, they both keep track of the state of the packets. Sender knows the packet is delivered, receiver knows the packet is already delivered, processed, so it can ignore the duplicate packets. I'm going pretty fast, I know, I'm sorry about it. I just want to finish this so we can stay schedule. But the good thing is here, about this tree scheme, I may refer to this come here, talking about it in further classes. But anything else that I just mentioned, don't ignore, but it's not going to bother you for the rest of the course. So at least one schemes for packet delivery, okay, work in a way that it's the simplest schemes for handling failure. So how it works, client stub waits for a response. So I send the package and I wait for you to respond, okay? I wait for acknowledgement. And if I don't receive the acknowledgement, okay, after certain times, I'm going to repeat that. So it's exactly like what I do here. For example, I say, I don't know, David, are you getting what I'm talking about?
Yeah.
Okay, so I received acknowledgement. Okay, so I'm not going to repeat that because I know the message is delivered, right? Because I got the acknowledgement. But if I say that, no response, I may repeat it again. No response, I may repeat it again. And I say, okay, maybe, for example, okay, Luis Falcon is not here. Maybe Luis Falcon is just in the meeting, but it's just another room, okay? So my message never delivered to it. So I can, after a few time of trying, I return an error and say, okay, Luis is not paying attention, okay? He's not here. So for example, this can be an example. Client server, I want to debit $10 to my account. I send that request. Maybe the server got the request, processes, and the acknowledgement. I don't receive the acknowledgement. The packet is dropped. I wait for the certain times, few milliseconds or whatever it is. No acknowledgement. I retry again. This time I get the acknowledgement, so I know the message is delivered, right? At least one time to the server, right? So that's basically one way. So let's look at another like example. I have two different like requests. I want to put 10 in the X. Then in the second comment, I want to put value 20 in my variable X. I send it. I get the timeout. I send it again here. Then the acknowledgement arrived. Okay. Then I send the second argument. Then I get the acknowledgement. So X value for me is 20. In the server also is 20, right? Because server put the X in 20. But things can go wrong. For example, I sent first request, put 10 in variable X. The message never arrived to the server. I wait, I don't receive acknowledgement. I send it again, put 10 in X, acknowledgement, okay, everything perfect. Now put 20 in variable X, everything perfect. I get acknowledgement. So for me as a client, I know the value of X is 20, right? Because I get the acknowledgement. But this first packet that I sent earlier arrived to the server for any reasons later than I expected. So server is going to receive this command, put X in 10. So the server is going to put X in 10, 10 in X. Sorry. Okay. So now client think, whatever. Let's say it's a bank account. You have $20 in your bank account. Server thinks you have $10, or whatever is that. So there are these type of issues. Okay. So is this method at least once ever okay? Yes, it can be okay if they are read-only operations with no side effects. So that's what Paul was talking about write operation, read operation. They really matters. Later we're going to see why it matters, why sometimes we deal them differently. If you have a write, if you're writing some variables, I might deal with that request differently when you are reading the variables, okay? So those are important. So for reads, at least once is okay. You can do that without any problem. Also, it's fine if the application has its own functionality to cope with duplication and reordering. So if the client can deal with those reordered message arrival, it's fine. We can go with this method. There is another one that most ones. I'm gonna go fast. Please, a little bit more, bear with me. So the idea is server RPC code detects duplicate requests. Because here I'm not going to wait for acknowledgement. I'm going to send it few times for the message to be delivered by the server. So the server might receive a duplicated request, okay? So I say put value X in 10, put value X in 10, put value X in 10, put value X in 10. Of course, I don't want all those requests, because if they are duplicated, to be repeated in the servers. I don't want to waste the server resources to doing something over and over for no reasons. So there should be some duplicate request detection mechanism in the server side. But we sometimes do legitimately ask for repeated requests, right? I want to read this document. I want to again read this document. I want to again read this document, or I don't know. I want to write this line. I want to do this again, do this again. Sometimes those type of requests is legitimate. Not always they are duplicated and illegitimate. So in order to do that, solve that problem, client can include some unique transaction ID with each remote procedure calls. So client use same basically transaction ID for retransmitted requests. So I have this request, I'm transmitting it 5 times. So I put same transaction ID for all of them. So the server, when receive those, they can say, oh, this transaction ID is the same with this. So I already processed this. Just ignore this. Ignore this because the transaction ID is the same. So it's a way to make sure the server doesn't process an illegitimate duplicate message. In order to come up with that transaction ID, you have different ways. You can combine a unique client ID like IP address with current time of the day. You put the timestamp, mix it with the, I don't know, IP address, make it a hash, send that to the server as a unique value. So you can do that different ways in order to come up with that unique transaction ID, because it should be unique, but you can have big random numbers using probabilistic that are generating unique random numbers for you. So, but another issue here at most ones is the server needs to keep track of the transaction IDs, right? I did this transaction ID 1, 2, 3, 4, 5, 6, 7, up to 10. I did all these 10 transaction ID. I have to keep a record of them, right? Because I don't want to do the duplicate process. But the problem is that old array will grow without a bound. How long is server going to keep these transaction IDs? Keep a record of this. So that can grow beyond bound, without bound. Let me see what's. So sometimes one solution for this can be how to say, a combined acknowledgement from the servers. There's different scenarios for this to overcome this. This basically significant overhead for the server side by maybe batch acknowledgement from the client that, okay, I'm done with this range of transaction ID, discard for the server. So the server doesn't need to keep track of all these basically transaction IDs. We are doing good. We are there almost. So we talk about this. It's the same thing. So the about the concurrent request, how to handle a duplicate request while the original is still executing. That can be another issue because I received transaction ID 5. I'm processing this, but for any reason, the processing is still going on, okay? I'm not done processing, me as a server. And again, I received another request. So the question is how I can deal with that, okay? That's one, another issue. So the idea can be adding a pending flag per executing remote procedure call. Adding that flag can help these issues. So basically, using that server waits for procedure to finish or ignores the procedure. Another problem can be server may crash, restart. So in that case, it's very important. The idea is server, if the server forget about the state, okay? The state of what state the server was right before the crashing, that can cause huge, huge problems, okay? For example, you do some sort of transactions, okay? Let's say you're withdrawing money from ATM, okay? You put your card, you put the money, I'm going to withdraw 5,000 peso from my account. You put the card. Of course, the ATM going to check your, check your, how to say it? Check your balance, okay? Check your balance and make sure you have 5,000 in your account before giving you the money. Check the balance, okay, say, okay, now reduce 5,000 from his balance, right? I reduce 5,000 from your balance. Right before I give you the money, the ATM is crashed. Okay, so what's happened to your money? I already told the server that I'm going to give you the 5,000, but I never did it because I crashed. A restart. So how am I going to deal with it? Did you lose your 5,000? I mean, you didn't. You never did it. Server thing, you did it. But so what's happening there? So the state is very important. The state of the procedure, the state of the machine, at what state is the machine. So those states need to be written in some sort of table that not just recorded in the RAM, more like on a disk. So after crash, you can come back and recover this state. We're going to talk about that quite a lot, about those state things. So I skip talking about more about that. So another one, so we talk about at least one, at most once, exactly once, okay? Exactly once. So for achieving exact once, we need retransmission of at least one scheme, because we need to make sure that the packet is arrived to the server. And also, because we do that multiple times, also we need the server to make sure having some duplicate message, like removal, sort of things like the at most one schemes. So it's basically can be happen at exactly one scheme for packet delivery, but it requires these two duplicate detection and also retransmission of at least once. Almost there. That's the slide. So exactly once for external actions. The idea, okay, this is the example I was talking about. So the whole idea here is you can achieve actually exactly once message, like a method of delivery, if there is no external action presence. Okay. External action presence is like, for example, in this example that I mentioned, me as an external action that doing some physical action with ATM. I'm the one I'm the one basically making I'm not problem there, okay? But if I was not there, the system could basically, if they don't need it to deal with me, they could recover from that using exactly one schemes. But if there is an external actions happening there, you cannot achieve exactly one's method of delivery. Summary, layers are our friends in the network. RPCs are everywhere. There are certain issues surrounding machine heterogeneity. Subtle issues around failure, we had at least once that was coming with retransmission, at most once coming with duplicate filtering. And then we talk about exactly once, that you need at least once plus at most once plus fault tolerant plus no external actions in order to achieve this type of packet delivery. Sorry, it took longer than I was expecting, but I promise you from the next class it will be much shorter, okay? And less me talking like crazy. The slides are available already for you.